In this video, we'll solve a problem about conveyance loss in an unlined parabolic canal. The problem states the conveyance loss in a 400-meter-long unlined parabolic canal with a top width of 1.5 meters when the flow depth is 0.8 meters, assuming a seepage and percolation loss rate of 3.33 times 10 to the negative 6 cubic meters per second per square meter is A. 1.5 liters per second, B. 3.5 liters per second, C. 6.1 liters per second, D. 7.3 liters per second. To solve this problem, we need to find the conveyance loss, which depends on the wetted perimeter of the canal and the given seepage and percolation loss rate. Let's break this down into steps. First, we'll determine the geometry of the cross-section. Then, calculate the wetted perimeter. Next, find the total wetted area along the canal. Finally, calculate the total conveyance loss. Let's start by visualizing the parabolic cross-section of the canal. We know the top width is 1.5 meters and the depth is 0.8 meters. Now, let's define the equation of the parabola. Since it's a parabola, we can write it in the form y equals a times x squared, where a is a constant we need to find. To make our calculations easier, let's define b as the half width of the canal, which is 1.5 divided by 2 equals 0.75 meters. Now, at the edge where x equals b, 0.75 meters, y equals the depth d, 0.8 meters. Substituting these values into our equation, 0.8 equals a times 0.75 squared, solving for a equals 0.8 divided by 0.75 squared equals 0.8 divided by 0.5625 is equal to 1.4222 per meter. Next, we need to calculate the wetted perimeter of the parabolic canal. The wetted perimeter is the length of the curve that's in contact with water. For a parabola, we can find this using calculus with the formula L equals the integral from 0 to b of the square root of 1 plus the square of the derivative of y with respect to x, dx. The derivative of y equals ax squared is dy slash dx equals 2x, so our wetted perimeter integral becomes L side equals the integral from 0 to 0.75 of the square root of 1 plus 2 times 1.4222 times x squared dx. With 2a equals 2.8444, we get L side equals the integral from 0 to 0.75 of the square root of 1 plus 2.8444 times x squared dx. This integral doesn't have a simple analytical solution, so we evaluate it numerically to get L side approximately equals 1.1474 meters. Since the canal is symmetric, the total wetted perimeter P equals 2 times L side, which is approximately 2.2948 meters. Now, we need to calculate the total wetted area along the entire length of the canal. The wetted area equals the wetted perimeter times the length of the canal. A wetted equals P times L equals 2.2948 meters times 400 meters, which is approximately 917.9 square meters. Finally, we can calculate the conveyance loss using the given seepage and percolation rate. The conveyance loss Q equals the seepage rate Qs times the wetted area A wetted. Q equals 3.33 times 10 to the negative 6 cubic meters per second per square meter times 917.9 square meters. This gives us Q approximately equals 3.06 times 10 to the negative 3 cubic meters per second, which is 3.06 liters per second. Looking at our options, the closest answer is B, 3.5 liters per second. To summarize our solution, 1. We found the equation of the parabolic cross-section. Y equals 1.4222x squared. 2. We calculated the wetted perimeter as 2.2948 meters. 3. We determined the total wetted area to be 917.9 square meters. 4. We calculated the conveyance loss as 3.06 liters per second, which is closest to the answer choice of 3.5 liters per second. This problem demonstrates how we can apply calculus and geometry to solve practical engineering problems related to water conveyance systems. The key insight was understanding how to calculate the wetted perimeter of a parabolic shape using integration.